How are you guys doing today? Pretty cold out there. Well, it's 8. Let's get started on redoing this one, or doing it more carefully. Okay, so we need to come up with a system of equations. And to do that, we're going to use this information here. So because there's a point of inflection at 126, I know that y of 1 is equal to 26, and that's going to be a plus b plus c equals 26. That gives us one equation, right? Okay, we get that y prime equals 3a x squared plus 2b x plus c. Okay, and we get that y double prime equals 6a x plus 2b, right? To have a point of inflection again at 1, we're going to focus on that right now. My second derivative has to be 0 when I plug in 1. That tells me that 6a plus 2b equals 0. Can we plug in 1 there? Okay. So that gives me that one and that one. I also know that this has to be equal to 0 when x is equal to 4 and when x is equal to -2. So y prime at, let's go with 4 first. So that's going to be 3a times 16 plus 2b times 4 plus c is equal to 0. And y prime at -2 equals 0 is equal to 3a times 4 minus 2b, well, plus 2b times -2 plus c. That's also 0. So we've got 4 equations, 4 unknowns, 3 unknowns. We should be able to solve this. Okay, so let's do this carefully. A plus b plus c equals 26. 6a plus 2b equals 0. I've got 48a plus 8b plus c equals 0. And I've got 12a plus minus 4b plus c equals 0. I'm going to try and solve for A and B first. So I'm going to get rid of C in one of these expressions. Let's get rid of C in the bottom expression, the middle expression. This one, we'll get rid of C here. And I'll get rid of C by taking this equation minus this equation. Okay. So we will have 60A plus 12B equals 0. And I have 6A plus 2B equals 0. Yep. All right, so we'll take 10 times this and take it away. We're going to end up with B equals 0 and A equals 0, aren't we? That's no good. Did I screw up one of my derivatives? 3 ax squared 2bxc. We put 4 in there, put 2 in there. Get a C. This is no good information, so that doesn't help. Because if I solve this, I get 0, 0, which probably is a solution. These two? That should just be a 6, but this is from that one right there. And this one is this minus this. 48 minus 12 is 60. 8 minus negative 4, sorry, 48 minus negative 12 is 60. That's not a minus negative 12 though, is it? That's okay. That's more helpful. So that's going to be 36. But that's still not going to help me anything. But it's less confusing than it was before. Because I still get 0 over 0. Or these things just cancel, right? 6 times the bottom one is the top one, which means that they're parallel lines. So any solution works. So those two, this guy and these guys together give me parallel lines, which doesn't help me in finding the solution. It just confirms that there is probably a solution. That's all that says. So we have to do something else. So let's try something else. Let's try like the bottom guy and the top guy together to get rid of C. So I will take the top one away from the bottom one, and we'll still have 6A plus 2B equals 0 from the middle one. But then I will have 11A from the top one, the bottom one minus the top one. And then the bottom one minus the top one is minus 5B. The bottom one minus the top one is 0. And then that's going to be minus 26. We good with that? Okay. Then I now can do a 2 equations, 2 unknowns deal, which is easier. So I'm going to multiply this guy by 6, this guy by 11, and then subtract. So I have 66A plus 22B equals 0. 66A minus 30B equals 156. Yep, 156. And then we'll take this thing away. It should be a minus there, right? and I get 0 there. I will get 52b equals 156, which tells me b equals 3. That's more promising than we had yesterday with the fractions over 11, right? Okay, so if b is equal to 3, then I can figure out what a is right away. 6 times a plus 6 equals 0, so a is equal to -1. So now I have a equals -1, b equals 3, and if I want everything to add up, I want a plus b plus c to equal 26. Better take 24 as c, right? So that this plus this plus this is 26. We all good with that? So let's check that this all works out. Were we told that a was positive? Okay. So I got minus x cubed plus 3x squared plus 24x is equal to y. Let's check and see that our derivatives work. So for the derivatives, y prime is equal to minus 3x squared plus 6x plus 24. So I need to factor this, I need two numbers that multiply to be negative 72, add to be six. So I'm going to take a positive 12 and a minus 6 are going to be those two things. So I can factor this. We go plus 12x minus 6x plus 24. I can factor out a minus 3x there. I can factor out a minus 6 there. I can factor out a minus sign and a 3x plus 6 and an x minus 4. So I could factor out a 3. Which tells me that we have roots, we have critical points at -2 and 4. So that checks out, that's good. We're gonna have maxes and mins. Y double prime is equal to minus 6x plus 6. Okay, so if I plug in -2, I get a negative, because that's going to be negative 18. No, that's going to be not negative. That's going to be positive. That's going to be 18. So we have a minimum at -2, y double prime at 4. That one's equal to negative 18. So that's a max at 4. And then it's going to be equal to, of 1 is equal to 0. So point of inflection at 0, or sorry, at 1. And we already checked that a plus b plus c equals 26. So I just want to make sure that my minimum's at -2 and my max is at 4. And that's what we started with. Max at 4, min at -2. So all worked out for us. Okay, where do you have questions on that? Just some algebra. It takes some time to do it carefully, but it's just algebra. And I went down a wrong path. We have to back up sometimes and try other things, but keep trying, you'll get there. Other things from 4.4 that you guys want to talk about before I move on to 4.5? Okay. This is Lehapital's rule. And indeterminate forms. Okay, I want to review some limit stuff just real quick before we do this. So limit review. So A sub n is a sequence that goes to A, and B sub n is a sequence that goes to B. So I've got two sequences. And they converge to A and B respectively. Then A sub n plus or minus B sub n, that's going to converge to A plus or minus B, right? If I have a plus, I add them together. If I have a minus, I don't. I subtract them. If I take a constant times A sub n, that's going to converge to the constant times A. If I have A sub n times B sub n, that's going to converge to A times B. A sub n over B sub n is going to converge to A over B, as long as B doesn't equal 0, right? And we skip B sub n equals 0 terms. So, which if B is not 0, you can only have finitely many B sub n equal to 0 terms. So you can skip finitely many terms. Okay, this is the one that I really want to talk about again. So if f is continuous, f of A sub n converges to f of A. So if f's a continuous function, you can do the function before you do the limit, or you could do the limit before you do the function. Either way is fine. So this is going to be key. This is an important one. In using Lehapital's rule. Okay. So let's state Lehapital's rule. So I've taken a specific input value, I put it into f and put it into g, and you get 0. F and g are differentiable on an open interval containing x naught. G prime at x naught is not equal to 0. for x in an open interval around x naught. But possibly 0 at x naught. So g prime of x naught could equal 0, but nearby it can't be. Does that make sense? This is kind of technical for the setup, but the punchline now. Limit as x goes to x naught, f of x over g of x is equal to limit as x goes to x naught of f prime of x over g prime of x, assuming that this limit exists. Okay, so let's see a quick application of this. So let's look at, say, f of x equals x minus 1, x plus 2, x minus 3, which is going to be x cubed plus plus 3 minus 6 is minus 3, and then minus 2 is minus 5. That's not right. Just add these up. Minus minus 2 x squared plus, that's the minus 5. And then multiply those together as plus 6. F, say g of x so that's x minus 1. I've got x minus 2, x plus 3, x cubed, add those, I get 0, minus 6, minus 9, plus 2, minus 7x, plus 6. Okay, so if I want to find the limit as x goes to 1 of f of x over g of x, right, f of x at 1 is going to be 0, g of x at 1 is going to be 0. They're both going to go to 0 there. Okay, so I could figure out how to factor this out, which I have already written down, and we factor it out. We evaluate it 1 up here, and we evaluate it 1 down here, and we get, if I put 1 in there, I get 3 times negative 2 is negative 6. I get minus 1 times 4, so I get 3 halves. Okay. So if I cancel these out in this fraction, I'm going to get 3 halves if I take that. So our goal is to get 3 halves. But I can't take this limit right away because as I go to 1, I get 0 over 0. So I would have to actually do this, factor it out, cancel, then reevaluate. Lehapital's rule lets us do this easier. So by Lehapital's rule, this is the limit as x goes to 1 of, well, let me make sure that I added these up right. So that's minus 7, that's plus 7. Yeah, that's minus 7, that's plus 7. Okay. So I get 3x squared minus 4x minus 5 over 3x squared minus 7. If I take the derivative of the top, I get that. If I take the derivative of the bottom, I get that. Okay. And now I'm going to evaluate at 1. If we evaluate at 1, I get 3 minus 1 minus 6. And here I've got minus 4, so that's 3 halves. So evaluating it after you take the derivative gives you exactly the same thing as if you'd gone through and factored everything out, canceled, and then evaluated before you took the derivative. That's Lehapital's rule. Another thing about Lehapital's rule is this doesn't say that when these limits go to infinity, that you can make it work for when they go to infinity as well, because you just kind of flip things around. So a sort of corollary, Lehapital's rule for limits at infinity too. So for example, if I want to take the limit as x goes to infinity, 3x cubed plus 2x minus 7, and I've got 6x cubed plus x squared plus x minus 8. This is going to look like infinity over infinity, right? And so what I can do is, if I have infinity over infinity, I do this little weird translation where I take the limit of 1 over x going to 0, because that's sort of the same thing as x going to infinity. And this is sort of why it works, but we don't actually have to go through why it works every time. And so if I flip over my inputs, it just looks like this. And now instead of going to infinity, this is going to go to like some constant. But what happens is I can just treat this like a y. Like I've switched variables. And I can differentiate both of those with respect to y, and we're fine. But the idea is I don't have to go through that process. I can just take this and go straight here by Lehapital's rule. Take the derivative of the top, and you get 9x squared plus 2 over 18 x squared plus 2x plus 1, and then you're still at infinity over infinity, so you use Lehapital's rule again. You get 18x plus 2 over 36x plus 2, and you're still at infinity over infinity. So you use Lehapital's rule again, and you get the limit of 18 over 36, and you get 1/2. Which, because this is such an easy one, and you just know that you take the leading terms and divide the coefficients, you still get 1/2. Right? But Lehapital's rule lets you do that here. Okay, there's some times where Lehapital's rule doesn't work. Like, let's look at this one. We'll go x to infinity again. You're gonna go e to the x minus e to the x with a minus sign on it, and e to the x plus e to the minus x. Okay, this looks like infinity over infinity because this goes to infinity, this goes to 0, so the top goes to infinity, this goes to infinity, this goes to 0, so the bottom goes to infinity. It looks like infinity over infinity, so we could just try and use Lehapital's rule. So by Lehapital's rule, this should equal limit as x goes to infinity of the derivative of this stuff, which is e to the x. That's going to be a plus e to the minus x, and this is going to be e to the x minus e to the minus x, which is the reciprocal, right? But then it's still infinity over infinity, so we do it again. E to the x minus e to the minus x over e to the x plus e to the minus x. And now we're right back to where we started, right? So if I just try and use Lehapital's rule right away on this one, it does not work. What we're going to do instead is we're going to make it look like infinity over infinity, but I'm going to manipulate it so that I don't have two terms that keep switching back and forth. So I'm going to multiply the top and the bottom by e to the x. Okay, and what happens there is that's going to be equal to, well, I get e to the 2x because exponent rules say addition of exponents, and then this is going to be minus e to the 0, which is 1, and this is going to be e to the 2x plus 1. And now we can use Lehapital's rule. So it's going to be 2 e to the 2x minus 0, and this is going to be 2 e to the 2x. And so that's all going to cancel, and this is just going to be 1. Okay with that? All right, so sometimes you have to do some weird stuff to get Lehapital's rule to work. And that's not really that weird. It's just do some algebra first so that it simplifies better when you're using Lehapital's rule. Kind of, if I can make some of the terms go to 0, that's really good, right? Because then you're working with a simpler function. So if you can make it so that you're going to have constants in your functions, that's going to simplify things so that you can use Lehapital's rule and simplify it. Okay, I talked about how limits of and continuous functions can kind of like interchange with each other, right? F of an equals f of a when f limit here. So if I take a sequence inside the function, I could have taken the limit of the function first when f is continuous. And we're going to use that here. And this lets us find these things called indeterminate forms, and then you use Lehapital's rule whenever you have an indeterminate form. So the indeterminate forms well, we already know 0 over 0. That's just straight up use of Lehapital's rule. We saw you could use it on infinity over infinity. You can use it on infinity times 0. Infinity minus infinity. 1 to the infinity. 0 to the 0. How many is that? 6? For some reason I think there's 7. Infinity over infinity, infinity times 0, infinity minus infinity. 0 over 0. Okay. They didn't talk about the last two. Let's call it those 6 for now. Okay. So let's see why this is true. Well, my main base form is 0 over 0, right? So I'm going to have to transform each of these other indeterminate forms into something that looks like 0 over 0 somehow. Okay. So to transform infinity over infinity, I write 1 over infinity over 1 over infinity. And that's the same thing as infinity over infinity. And this is equal to 0 over 0, right? So that sort of process where you flip, if this f of x, this is g of x, what you do is you write 1 over g of x, 1 over f of x. If I write it as 1 over g of x equals 1 over f of x, that gets me to a 0 over 0 form, but it's the same thing as f of x over g of x. Yeah. Sorry? So let's do an example. I'm going infinity over infinity. That's 0 over 0. Zero over 0. Goes to 0 over 0. Second x. 0 over 0. 0 over 0. 0 over 0. All I'm finding is a bunch of 0 over 0 problems. See what example they use. Okay, let's look at limit e to the x over x squared as x goes to infinity, something like that. Okay, right now it looks like infinity over infinity. So we're going to translate this to, this is the limit of 1 over x squared over 1 over e to the x as x goes to infinity. This goes to 0, this goes to 0. Does that make sense? Or what do you mean by flip the coefficients too? Yeah. So as x goes to infinity, this top goes to 0, right? The denominator still goes to infinity, but the fraction goes to 0. And so I could use Lehapital's rule on this. In this case, it's more complicated than just to use Lehapital's rule here, but and it actually probably doesn't work out very well if I use Lehapital's rule here, because now I get minus 2 over x cubed. That's increasing the power of x in this one. We don't really want to do that. And this just stays minus 1 e to the minus x, sorry, e to the x. Yeah, that'd be minus 1. E to the x still. So that just switches it. That keeps that thing the same, but makes that denominator more complicated. So in this case, I probably wouldn't rewrite it like that, but a lot of cases, you might want to rewrite things like this so that you can actually take derivatives and we get things to cancel. Okay, so let's see one where, so if I take the limit as x goes to infinity, let's say x goes to 0, of well, let's go x goes to 1. Make things more interesting. So something like this. On the top, that fraction goes to infinity because the denominator goes to 0. And here, this fraction goes to 0 because that denominator goes to 0. Okay. So to get this to go to 0 over 0, I'm going to rewrite it as limit x goes to 1, e to the x minus e over x squared minus 1, right? That's the same expression here, only I've changed the tops and the bottom. Okay. And now I get 0 over 0. And by Lehapital's rule, this is going to be the limit e to the x. E is a constant, so its derivative goes to 0. Here, that's 2x as x goes to 1. So this is going to be e over 2 is what my limit's going to be. Okay. So that was infinity over infinity. Let's do like an infinity minus infinity. I know I saw one or two of these. So let's do limit x goes to infinity, ln of 2x minus ln of x plus 1. As x goes to infinity, this goes to infinity minus this thing that also goes to infinity. So we've got an indeterminate form here. Okay. And so I could do, well, there's a couple things we can do. Let's do the one where we're going to transform this limit, not using the algebra. The easy thing to do in this case, but not the one that I want to talk about, because this other technique works more generally. When you have the natural logs here, the easy way to do this is write it as limit x goes to infinity ln 2x over x plus 1. Since the natural log is a continuous function, This is the natural log of the limit x goes to infinity of 2x over x plus 1. And then you use Lehapital's rule there. ln limit of 2 over 1, x goes to infinity. So this is natural log of 2. Right? Okay. Otherwise, the thing that I would do with this is I'm going to call this limit L. And I have an infinity minus an infinity right now. It would be really nice to get this to 0 over 0 or infinity over infinity, so I can just like apply Lehapital's rule to the top and the bottom and go from there. So I'm going to take the natural log of e to the thing, right? If you interchange natural logs and e's, they don't change anything. And so I'm going to have sort of an outside function here of the natural log, and then on the inside, I'm going to have ln of e to the infinity divided by e to the infinity, and this is looking like infinity over infinity again, right? Okay, so let's see how that would process in this case. So I've taken this limit and I've called it L. And so e to the L is equal to e to the ln of 2x minus ln of x plus 1. And this is a limit. E isn't a continuous function, so I can do the e outside the limit, or I can do the e inside the limit. Then I can do the arithmetic here. And get 2x, do the arithmetic here, do x plus 1. And this is equal to, by Lehapital's rule, 2 over 1. So I know that e to the L equals 2, which tells me L equals the natural log of 2. Let me try and find one where I actually have to do that and I can't use just log rules. Let's try it on this one. Okay, if I put 1 in there, I get 1 over 1 minus 1, which is 1 over 0, which goes to infinity. If I put 1 into the natural log, I also get a 0. So this is this looks like infinity minus infinity 1. Are we okay with that? Okay. So what we're going to do is we're going to call this thing L. And we're going to take e to the L. And that's going to be the same thing as the limit as x goes to 1 from above, e to the 1 over x minus 1 minus 1 over ln of x. So far, so good? Okay. Then we're going to rewrite that as a limit of e to the 1 over x minus 1 over e to the 1 over ln of x. And then we can take derivatives here and here. Now this might be more complicated than it needs to be. There might be a better way to do this one too. We're just going to do a lot of techniques until we find things. Okay, so Lehapital's rule says we're going to take the derivative of the top, derivative of the bottom. And that just got really, really messy. And I think if I keep taking derivatives, it's going to get messier and messier. So this is probably not the way that we want to do this one. Let's try it a different way. Let's find a common denominator. And I find a common denominator. The top goes to, that goes to 0, that goes to 0. The top goes to 0, the bottom goes to 0 as well. So it looks like 0 over 0. Let's use Lehapital's rule on that. That looks like it will actually simplify things. Product rule here. End up with that. And this still goes to 0. This still goes to 0. Let's simplify that before we do more derivatives. And then here. End up with that. Those x's will cancel. Top goes to -1 by Lehapital's rule again. The bottom is going to go to 1 plus derivative of x, natural log of x, is x times 1 over x plus natural log of x. So this is, those guys cancel. Limit x goes to 1 from above, -1 over 2 plus natural log of x, which is minus 1/2. Good. Okay. Let's try. That was, we've done a infinity over infinity, infinity minus infinity. I haven't done a 0 times infinity yet. Okay, sine of x as x goes close to 0, this goes to 0, right? As I plug in really small values close to 0 into the natural log, it goes to negative infinity. So this looks like 0 times negative infinity. We good with that? Okay. So what we're going to do, we're going to rewrite this so that it either looks like 0 over 0 or infinity over infinity. And the first thing that I think I want to do is I want to rewrite this. I would rather not take the derivative of 1 over the natural log, so I'm going to try and keep that up top. And then I'm going to divide by not the sign, but 1 over the sign. Okay. So the same trick that I talked about when we switched infinity over infinity to 0 over 0, you bring one of the functions down into the denominator by writing it as a reciprocal. Okay. So we write the reciprocal of sine in the denominator so that it looks like you're multiplying by the sign, but you're actually dividing by the reciprocal of the sign. And now this looks like infinity over infinity. And I would probably rewrite this as limit x goes to 0 from above natural log of x over the cosecant of x, because we have derivative rules for the cosecant, where I would probably want to be tempted to use the quotient rule on 1 over the sine. Okay, so by Lehapital is ruled in. This is the limit as x goes to 0 from above of 1 over x over, what is the derivative of the cosecant? Yep, minus cosecant cotangent. Okay. And I still have issues, right? Because cosecant is still a sine thing, and cotangent, that's cosine over sine. And if the sine is going to 0, that's going to 0. So let's rewrite this algebraically. I can rewrite this with the x in the denominator, a minus sine up top, and a tangent up top, right? And now this looks like 0 over 0. So we could use Lehapital's rule again if we wanted here. But the first thing I noticed before we do that is that we already know what the limit of sine of x over x is, right? Remember from 3 weeks ago or 6 weeks ago or whatever it was when we were doing sine of x over x stuff? This goes to 1, right? You could do it with Lehapital's rule too here, but this guy goes to 1. And the tangent of 0 is 0, so this is going to go to 0. So a lot of times you have to do this algebra manipulation with these things too. Let's try one of these where I've got maybe a 0 to the 0 thing, or a, oh, that's the other one. Okay. I had 1 to infinity, 0 to 0, infinity to 0. Okay. These are all indeterminate forms because if you follow one rule, it's going to be one thing. If you follow another rule, it's going to be another thing, right? 1 to any power is infinity, but if I take things that are bigger than 1 an infinite number of times, even if they're really, really close to 1, it's going to end up somewhere between 1 and infinity. That's kind of how that works. Or if I think things that are just slightly smaller than 1 an infinite number of times, you might think it goes to 0. All right. 0 to the 0, well, 0 to any power is 0, but anything to the 0 power is 1, so which rule there do I use? Infinity to anything multiplied any number of times is infinity, but if I don't multiply it any times at all, I should get 1, so which rule do I use there? Right, that kind of stuff. This is like, which of these two infinities is bigger? How much bigger? Multiply by infinity, you always get infinity. Multiply by 0, you always get in 0, which works. Same type of stuff there. Okay, so there is the last one. And let's do a 0 to the infinity one. So let's look at limit, say, x to the minus 1 natural log of x as x goes to 0. We better go from above so that it's defined in there. So I've got 0 to the infinity here. Oh, this is 0 to the 0, isn't it? Because natural log of 0 goes to negative infinity. So this is 0 to the 0. So what should I do to get rid of the 0 to the 0? We're going to take the natural log of everything. And we're going to take the natural log of L. And that's the limit of the natural log of x to the minus 1 over natural log of x. X goes to 0 from above. And so if I use my natural log rules, this is the limit. X goes to 0 from above, minus 1 over the natural log of x times the natural log of x, which is limit x goes to 0 from above of minus 1, right? Those natural logs cancel. So that's just minus 1, which tells me that the natural log of L equals minus 1, tells me L equals e to the minus 1. So the limit of this is e to the minus 1. I didn't even have to use Lehapital's rule there. But that's the transform that you're going to kind of look at. Let's try. That looks like 1 to the infinity. Yeah, we'll try limit x to infinity, x plus 2, x minus 1 to the x. This looks like infinity over infinity, which could go to anything. And in this case, that infinity over infinity goes to 1, right? We know that I take the leading coefficients of this rational thing inside the parentheses, I go to 1. So inside here, I go to 1. This goes to infinity. So this looks like an indeterminate form of 1 to the infinity. Everybody on board with that one? Yeah, we're going to do the same thing again. We're going to take the natural log so that I can get rid of this exponent. I have that exponent up there. It'd be nice to bring it down so it can be changed into a division or something like that. So we're going to call this L. We're going to take the natural log of L. That's going to be the limit. X goes to infinity of x times the natural log of x plus 2 over x minus 1. Okay. And now this looks like infinity times 0. So we're going to rewrite this. So it looks like 0 over 0. And then I can use Lehapital's rule. Let me rewrite the thing inside here so that it's easier for me to take a derivative. That's one way, and that's going to be the way that we choose this time. The other way, you could rewrite this as 1 plus 3 over x plus minus 1. That's one way you could write it too and leave that inside. But let's rewrite it this way. Okay, so now that I take Lehapital's rule, I've got 1 over x plus 2 minus 1 over x minus 1 over 1 minus there. Okay, I've got rid of the natural logs. All I'm doing was working with a rational function now, right? And that's nice. I like to work with rational functions. They're easier to work with. So this now, I can simplify everything, find a common denominator, all that. So I've got an x minus 1 minus an x plus 2. So it's going to be a minus 3 over x plus 2, x minus 1, over 1 over x squared with a minus, so those become a plus. And then we're going to flip this and put it up here. And that's going to be 3. The leading coefficient down here is going to be x squared. The leading coefficient up there is 3x squared, so that's going to go to 3. And so I know that the natural log of L equals 3, which tells me L equals e cubed. Where do we have questions on that one? Get time for at least one more. That one's similar. For the limit x squared ln x as x goes to 0 plus. Which indeterminate form do we have? Yep, 0 times infinity. Okay. So we rewrite that by making it look like either infinity over infinity or 0 over 0. Okay. I don't want to put a natural log in the denominator particularly before I take a derivative, so I'm going to keep that one up top. You get ln of x over 1 over x squared. And then by Lehapital's rule, you get that limit 1 over x. The derivative of that is minus 2 over x cubed. Okay. I can simplify this just with some arithmetic. I'll get x squared over minus 2. And as x goes to 0, this goes to 0. Yeah. Let's try a different one. Let's try limit x ln of x with the ln of x squared. Okay, so I still go to 0 times infinity, right? But this infinity is like double infinity. So this is like 0 times infinity squared in some sense. So let's see what this one does. So I'm going to rewrite this still as ln of x squared over x, 1 over x as limit x goes to 0 plus. And then by Lehapital's rule again, this time I get 2 ln of x 1 over x over minus 1 over x squared. So this is the limit. Do some arithmetic. One of these cancels with that. So I've got 2 ln of x over minus 1 over x now. We all good with that? Okay. And then I get to do the exact same thing, Lehapital's rule. Two 1 over x, and then I've got a plus 1 over x squared again. And now this is going to be a limit x goes to 0 of 2x, which is equal to 0 still. A lot of these just take lots of practice. You got to see them, try them, figure out how to do the algebraic manipulations to get them into the form that you want. It takes practice. Any last questions before I let you go? Okay. Come with questions tomorrow. I'll see you guys then.